Right, everyone? So we're going to continue now with the second section of the class. So the midterm wasn't too bad, right? People are undecided yet. But that's all done and dusted now. But we're still going to think about those same ideas. We're still going to talk about albedo. We're still going to have to understand that the climate is changing. But we're going to move on now from snow, which is that sort of frozen water in precipitation form. And we're going to talk this week about permafrost, which is something that, if you think about it, it makes a lot of sense that when ground gets so cold, it freezes. But obviously, we live in a place where it doesn't often get that cold, and so it's not something that automatically occurs to us as something that is really important for the Earth system, but it is. And so this photo here doesn't show permafrost necessarily, but it does show that you can get these big masses of frozen ice as well as frozen soil underneath what looks like sort of nice soil that is growing, sort of vegetation. So it's up there, it's underneath a lot of our high latitude land area. So it's worth understanding. Okay, so what is permafrost? Permafrost is ground that may or may not contain water, because you can have just completely dry ground as well. But it has been below 0 degrees Celsius, so below that freezing temperature for more than 2 years. And it can be anywhere from 1 meter thick to 1,400 meters thick, so over 1 kilometer down of frozen soil and sediment in some places near the pole. And then we have a couple of other things that we use when we talk about permafrost. We talk about the active layer, which is that very top layer on my diagram, and that's the layer of ground which thaws out in the summer and freezes again in winter. And why do you think it might be called the active layer? Why might it be called the active layer? Because it's melting, and what does that fact that it's above 0 degrees Celsius, what might that allow us to have going on? Life, absolutely. We have active life processes going on there. So we have plants growing in it, we have microbes that break down organic matter. We have active processes going on in that layer, at least in the summer, and then it freezes again in the winter. So that's our active layer. And then this funny word, talic, which I think is a Russian word, because a lot of what the research that was first done on this was done in those areas. And that, it just means thawed out permafrost. So permafrost that is now above 0 degrees Celsius again. And it can be because it's deep, or it can be a little pocket within the permafrost itself. Okay? So is everyone happy with my definitions? Because we're going to use those a lot today. Yep? Right. So this is what it would actually look like. So if we cut down and sort of carved ourselves out a trench in one of these areas, this is a pretty thin layer of permafrost. But you can see that nice brown looking normal soil at the top. That's our active layer. And this must be in the summer. And then you can see that white color showing the ice of that permafrost layer. And it's not that deep, it's sort of that deep or so. And then underneath again, you can see that again we have unfrozen ground. Okay? So that's what our permafrost would look like in real life. So let's introduce some terms that we use to describe how much water we have in our soil. If we're going to talk about frozen soil, then it's nice to know what we can use to describe that. And we have two things that we use to describe how much water we can get into our bedrock and soil. So first of all, that's called groundwater. It's basically all the water we can get into the ground. And we then have porosity. So porosity is basically how many pore spaces you have. So how much open space exists in your rock. And then lastly, we have permeability, which is basically just a sense of saying how connected are those different pores. So for example, if we look at my different examples here on the very left, we have something that has quite a lot of pore spaces in it, and those are all connected together. So an example of this one might be like sand at the beach. You know, if you pour water on sand at the beach, it just soaks straight in, right? It goes really fast, and that's because all of those grains have more or less the same size. And so they don't sort of pack tightly together, they have lots of these open spaces, and all of those open spaces are connected together. So it allows lots of water to be in that on those spaces, and it also allows it to flow really easily. In our second case, in this case, we have lots of different grain sizes. We have some big ones, some small ones. And so what happens is those small ones actually pack into the spaces between those large grains. And what that does is it reduces our porosity. So our middle picture there has a low porosity. We just can't get much water in there to begin with. And it still might have a relatively good permeability, but it's going to be more difficult to connect those spaces. And then my last example is one where we have a lot of space in our rock. We have those really big spaces. But in this case, because we've had that water in those spaces, we might have crystallized out something like calcium carbonate, whatever else, and it's sealed off those different spaces. So they no longer connect to each other. So even if there's lots of pore space and there's lots of space for water, it's not going to be able to move through that rock or through that soil particularly easily. Okay, does that make sense? Yes? Okay, so prove to me it makes sense. So what about concrete? Does concrete have a low permeability or a high permeability? Does it have low or high permeability? Any more? Okay, let's take a look. See if we agree. So 83% of us agree, low permeability. That's right, because what happens if we pour water onto concrete? Does it soak through it? Hopefully not, right? It's what our buildings are made of. We don't really want it to be particularly permeable. So that's right, we have low permeability for concrete because as we pour that water on, it flows off. It doesn't flow in through that concrete. And it's one of the interesting things that now engineers are actually trying to come up with low permeability concrete that we might be able to put in areas like parking lots. And that would allow rainwater to actually sink into the ground. Whereas right now, all of that rain that falls, well, when we have rain, all of that rain that falls on our parking lots just runs off into our sort of drainage system, and it doesn't replenish our groundwater, which sort of vegetation and we want to use. So it's engineers are doing clever things there. Great. So, second question of the day. Lots of questions today. Would permafrost have a high or a low permeability? What do you think? Any more votes? I think that's more or less everyone. All right, let's see. Oh, a little bit more of a debate this time. Turn to your neighbor, turn to the people behind you, ask them what they put, why they put it, see if you can persuade them that you're right. Last few seconds, so if you haven't voted, take the opportunity to. Okay, let's take a look and see how whether your neighbors have been persuasive or not. Okay, so we have had quite a switch. And the good news for me is that it's the right way. It would have low permeability. So let's think about this. If you had a block of ice and you poured water onto it, would it go through the ice? No, it's going to run off, right? And so the idea is even if our soil had a lot of porosity and had a lot of pore space, if those pores are filled with ice, then that's still not going to allow water to move through that permafrost. Does that make sense for those 25%? So even if we have porosity, if those pore spaces are filled with solid ice, then we're not going to be able to have movement of water through that. So permafrost layers are nice impermeable layers, and that's something we're going to talk about on Friday when we talk about some of the consequences of thawing out our permafrost. Because before, where we had nice lakes which were sort of kept at the surface by this impermeable permafrost layer, in Alaska now, if we're melting or thawing through that permafrost, then that water can drain down and drain away, and that's a problem for some of the villages that rely on these lakes as water supplies. Okay, great. So let's go back to thinking about permafrost. And we have different ways of describing permafrost and the bands that it forms based on how much of it there is there. So up at the top, you can see that continuous permafrost is basically thick, unbroken permafrost. If you look out at your landscape, you can be pretty certain that there's permafrost under every single square meter of that. And obviously, that was much more likely to occur up near the very coldest regions of the pole. So for example, down here, we've got our greatest thickness of permafrost, and it's also continuous across the landscape. But then as we move sort of further south towards our equator, then we get into different amounts of permafrost. We first of all go into discontinuous permafrost, which is still mainly permafrost, but a few patches of thawed out permafrost, of unfrozen ground in between, okay? And so that might be under lakes, where that nice water can absorb lots and lots of energy, and so it keeps the ground underneath it a bit warmer. Or south-facing slopes. All of you know that you want your sort of bedroom to be on the south-facing side because you get lots of nice warm sunlight coming in. And it tends to be thinner and younger than the continuous permafrost. It tends to have formed within the last few thousand years rather than sort of tens of thousands of years ago. And then lastly, as we go even sort of further south or further towards the equator, we get sporadic permafrost. And now mainly our ground is unfrozen, and we just get little patches of permafrost, for example, where there might be shade, maybe on the north side of mountain slopes, things like that. Okay? So continuous, discontinuous, and sporadic. And if we look at a map of that, so again, we have our funny maps showing different angles. So again, the center there is the North Pole, and then we've got Asia, Europe at the bottom, North America on the left there. And you can see that, unsurprisingly, our dark-colored blue, which is our continuous permafrost, is mainly closest to the North Pole. And then we've got that sort of paler blue, which is discontinuous on the outside. And then lastly, we've got our isolated patches. And you can also see that in North America especially, we get a little line of sporadic permafrost running down the middle there, even further south. What is that probably following? What geographic feature is that? The mountains, the Rockies, absolutely. So where we're nice and high up. Okay. And what big mountain range are we looking at over here on this side where we have permafrost? The Himalayas, absolutely. You're all going to know what the mountain ranges are by the end of this class. Okay. And we even actually get some permafrost under the ocean in the Arctic Ocean. And it's not because permafrost will form under the sea. It won't. It needs to be exposed to cold air temperatures in order to form. And it formed there because during the last ice age, we had so much ice on land that our sea level was 120 meters lower. And that exposed a lot of this, what's now sea floor, to the atmosphere, and permafrost formed there. So we still have this permafrost which is left over from that last ice age underneath parts of our Arctic Ocean where it's shallow enough. Okay, so we really get permafrost wherever that summer heating doesn't completely melt through our soil. And so I have a question for you. I keep using this word thaw. What's the difference between melting and thawing? What's the difference? Why would I use one rather than the other? So I have another question for you. If I get a lovely frozen turkey for Thanksgiving and put it on the side in my kitchen, is it going to melt? No. I'd be very worried if my turkey started melting. It's going to thaw. So what's the difference there? Why do we use the different words? Sorry, say that again?
Does the melting go to a full liquid?
Absolutely. So you're absolutely right. In melting, we're changing from a solid to a liquid. Ideally, our turkey doesn't change from a solid to a liquid as we sort of warm it up. It should stay a solid. But instead, it being a solid below 0 degrees Celsius, it's a solid above 0 degrees Celsius. And the same is true for our permafrost. The ice in those pore spaces might melt, but the soil as a whole, as that solid changes from below 0 degrees Celsius to above 0 degrees Celsius, we call that thawing. And I try and always use the right one, but you are allowed to shout at me if I use the wrong one. Okay. So my second question for you is, what could cause our permafrost to thaw out? What could provide that energy? Sorry?
The summer.
The summer, absolutely. And what in particular about the summer?
It's warmer during the summer.
It's warmer during the summer, absolutely. And where is that energy coming from?
The sun.
The sun, okay. So yeah, absolutely. We're getting that much more of that energy in the summer from the sun. Because remember, we're tilted towards the pole, towards the sun, and so we're getting more of that radiation. What else though? Why are we not frozen soil all the way from the surface, right the way down, like kilometers and kilometers and kilometers? The core. What's specific about the core? It's hot, absolutely. It's hot, okay. They're not tricky questions today, I promise. And so, absolutely, the core and the center of our Earth is hot. It's hot partly because of the leftover heat from the formation of the Earth, but mainly actually today, a lot of that heat comes from radioactive decay. So just like we use nuclear energy from the radioactive decay which produces heat, that's happening within our Earth. And when that radioactive decay process happens, it produces heat. And that heat can't go anywhere. In fact, it's trying to escape out to space. So very, very gradually, we are losing heat from the Earth. It's sort of moving out from the core, and it's trying to escape out to space. And so has anyone ever been in a really deep mine? No? Only me? Okay, fair enough. It gets hot. It gets hot as you go down. If you ever sort of see some of the working conditions in some places where you have these really deep mines, it's miserable because it is really hot down there. We have what we call the geothermal gradient, okay? And that means that it gets hotter as you go down towards the center of the Earth. Okay, so absolutely. So melting is a phase change from solid to liquid. Thawing is just changing that solid from below to above freezing. And our energy can come from solar radiation, so our permafrost can warm from the top. But also we have this geothermal energy escaping from the Earth. It's not nearly as important as what comes from the sun, but it still is important for our permafrost. Okay, so as a reminder, because I know that people haven't seen this for a while, we have conduction, convection, and radiation. Conduction is movement of energy through a solid. It's one of the reasons that if you have stupid pans like I do and have metal handles on your pan, even if the handle isn't immediately above the flame, it gets hot, right? And you can burn yourself by picking it up. And it's not because the pan is moving around in any way. It's just because the energy is transferred from molecule to molecule, and that can make it all the way out to the handle. The second way that we can move energy around is by convection. And convection works because as you heat something up, so in our example, the water in the pan, as we heat that water up, those little molecules get more and more and more and more energy, and they move faster and faster, and they end up occupying more space, and they become less dense. And we know that more dense stuff will sink, and less dense stuff will rise. And so that warmer stuff will rise, and it will hang out at the surface for a while until it cools down a little bit, and then it's more dense again, so it will sink. And we form what we call convection currents. So where we have rising warm air or water, and then it sort of cools down, and then it sinks back down again. Okay, so that's what's happening in your pan. And then lastly, we have radiation. And radiation doesn't need anything in order to transfer that energy. So with convection, we're getting energy moving by moving the substance itself. Conduction, we're getting energy moving through a solid. But radiation doesn't require any molecules or anything there to transmit that energy. Okay? So, obvious question of the day. How does energy travel from the sun to reach the surface of the Earth? I almost feel embarrassed asking this one. Last few seconds? Right. I think that's everyone. Good. 88% of people agree with me. Radiation is the most important one because what's it traveling through to reach us? Space. Okay? And there's not a lot of stuff in space. So we can't rely on this conduction or convection process to transfer that energy. So, second obvious question of the day. How does energy therefore travel through our soil? How does it travel through soil and rock? So for example, how is that energy moving from sort of the mantle through our crust and creating our geothermal gradient? Good, we more or less agree again. So conduction, because the soil itself isn't moving, but the energy is having to move through that solid in order to create our geothermal gradient. Great, okay, so we're on the right track. Now, dig out your paper, because we are going to draw some graphs, which I know everyone is excited about. So what we're going to do now is take a more careful look at what happens to our temperature as we go through the soil. So we're going to look at something called soil temperature profiles. It's also going to be called trumpet diagrams for a reason that we'll see at the end. And so last year I just sort of put up the figure and everyone got utterly lost. So this year we're going to try actually drawing it out together. Okay? So on my x-axis at the top I have temperature going from extremely cold, -15, to nice and comfortable at +15. So 0 runs down the middle there. And then on the y-axis I have depth of my soil. So 0 is the soil's surface, and 40 meters is sort of 40 meters down in the soil. Okay. So what I'm going to say first is that my annual temperature, my annual average temperature at this particular location is going to be -5 degrees Celsius. Okay? So I'm going to mark -5 degrees Celsius. What happens to the temperature of my soil as I go deeper? Does it get colder or warmer? Warmer, because of our geothermal gradient. Remember, we have that heat escaping. So I'm going to massively exaggerate that, okay? But you don't necessarily need to. So I am going to say that we're going to get warmer. I forgot my ruler, so this I'll have to do. We're going to get warmer as we go down, okay? Okay? So we're going to get warmer as we go down. And the important thing about geothermal gradients is that this slope, this angle of this slope, stays the same. So if my annual average temperature changes and perhaps becomes -10 degrees Celsius, then that angle would stay the same. I would just draw it over here instead. Does that make sense? Yeah? Okay. So that's my annual average temperature. And that's all very well, but we don't really care about the annual average. We want to know, well, how warm is it in summer? So in the summer, is the top of my soil going to be warmer or colder? Warmer, thank you, absolutely. And so how much is that going to warm, though? Is it going to be just the top that warms, or are we going to warm the whole 40 meters all at once? Just the top, absolutely. We're only really going to affect the very top, because that conduction process is relatively slow. And so you can imagine that, say, if I take red to be my summer temperature, then in the summer, what my temperature profile might actually be more like is maybe this. It might be, say, sort of 5-6 degrees in the summer. And that will decrease down until at a certain point it will start increasing again because of that geothermal gradient. So that's my summer. It's my high temperature in the summer. This is my annual average. What do you think this might look like if I tried to draw the profile for the winter? Is it going to be warmer than my annual average or colder? Colder, okay, good. And again, it's not going to affect the whole thickness, it's just going to affect the top. And so again, we're going to sort of part in this sort of direction, and I'm going to have really cold winter temperatures of like down to -15, okay? So that shows what my winter temperatures would be like. Okay. So now you can see why it's called a trumpet diagram, because it sort of does that, it flares out at the top. Okay. So if we want to know what our thickness of permafrost is, we can now really easily work it out straight from our graph. Okay? Because what we're going to look at is where my lines cross 0 degrees Celsius. So what depth, what's the greatest depth that my permafrost is? Where is the soil below freezing, the deepest point? 35. So if we go down to 35 meters, you can see that below 35 meters, it's ever so slightly warmer than 0 degrees Celsius. And above 35 meters, it's ever so slightly colder. So if I'm looking for where my permafrost is going to be above this line, okay? So this is my maximum depth of my permafrost, okay? Or the base of my permafrost. Where is the top of my permafrost going to be? Which line do you think I have to look at? The summer, absolutely, the summer one. Because remember, that sort of, what we're interested in is what depth during the summer is that soil still going to be frozen. So of course it's all going to be frozen in the winter, right? It's going to be minus 15 degrees Celsius. It's really cold. What we care about is, even in our warmer summer months, what part of the soil is still frozen? That's going to be our permafrost, our permanently frozen soil. Does that make sense? Yeah? So what depth is my, sort of the top of my permafrost going to be?
7.
I like 3 a lot better than 7 or 8, okay? Everyone's looking stunned still. But you can see that now this is where my temperature, my summer temperature, crosses 0 degrees Celsius. Above that, my soil is warmer, okay? Below that, my soil is colder. And so below this point where it crosses that 0 degrees Celsius, I'm going to have permafrost. Yes? Great. Okay. So here, I'm going to draw the top of my permafrost. Okay? My unintelligible writing. Okay? So our permafrost actually stretches all the way from there down to there. Okay? So is everyone roughly following me so far? Or do you want me to run through it one more time? Well, there's no frantic yells for one more time. Okay, in that case, you know you're not going to escape that easily, because you know what will come next. In groups of 2 or 3, prove to me this concept and how those lines would change. So the first task, and the TAs will stand up and wander around and help you out. What happens if my annual average temperature stays the same? So you can see that my straight line there. What happens if my annual average temperature stays the same, but my summer temperature increased? What would happen to the depth of the active layer and the permafrost layer? In part B, I want to say, well, what happens if all of my temperatures get much warmer? Okay, and remember that geothermal gradient has to stay the same angle. So what would happen to my depth of permafrost, and what would happen to my active layer? And what would happen if my annual average temperature, so that middle, that dotted line when it hits the surface, what happens if that was above freezing, so above 32 degrees Fahrenheit? Okay? So I'll give you a few minutes to think about this and speak to your neighbours. Okay? The people I spoke to were really on track. I'm very impressed. So yeah, absolutely. Let's think about the first one. So our annual average temperature is staying in the same place. Everything else is staying in the same place. The only thing we're changing is our summer, maximum summer temperature. So what's going to happen to the depth of my active layer? It's going to increase, right? It's going to move down, because if I redrew, let's see if I can do funny things on my PowerPoint slide. Maybe not. I thought it had a pen thing. But if I redrew this, basically that line, instead of going and following this path, it would actually probably go like that. And so it would go across that 30 degrees Fahrenheit line lower down. Are we doing anything to the base of our permafrost if we're just changing our summer temperatures? No, right? Is it still, those other lines are staying in the same place. So now let's think about part B. So what happens if we just shifted that whole sort of trumpet shape a couple of degrees further over? What are we now doing? Yeah, absolutely. Now we're going to be thawing out the bottom, because now our geothermal profile is going to also be shifted along. And so it's going to cross that 30 degrees Fahrenheit slightly further up. And so if we increase our annual average rather than just our summer temperatures, we're going to be thawing out our permafrost from the base as well as from the surface. And this is what's happening today. As we increase our annual average temperatures, we're going to be thawing our permafrost not just from the top, but also much more slowly from the bottom as well. Okay? And what happens to our thickness of permafrost if our annual average temperature is above freezing? Do we have any permafrost? No, because if our annual average temperature is above 30 degrees Fahrenheit, silly scale, then it won't ever cross that 32 degrees Fahrenheit line. So we're not going to ever have permanently frozen soil. We might get a little bit that's frozen in the winter, but it's never going to stick around through the whole summer. Does that make a bit more sense now? I think this is a challenging thing to understand at first, but once you get it, it makes a lot of sense. So you'll have a chance to practice this in discussion again next week as well. Okay, I will also happily go through this in office hours anytime for someone that's feeling utterly lost. So, my second tricky question. So our permafrost depth, this is great if that's really all that's affecting it. So if air temperature was the only thing that really mattered, then that's how it would be. But we also have a lot of different other factors that can affect our permafrost depth. So first of all, our temperatures, but also snow cover. So I have a really evil question. I always have to have one evil question per lecture. So my really evil question of the day is, what would thick snow cover do to our permafrost thickness? Do you think it would be more likely to increase our permafrost thickness or less likely to increase our permafrost thickness? So I'm going to give it a couple of minutes to talk about it, pin down a TA, ask them what they think. Okay, so let me know if you think you have an answer. Okay, so I think we'd better move on. So if you want to give me your answer, your best estimate for what you think might happen. Okay, so let's take a look and see if we, it's a 50-50 chance, right? So most people say that it would be less likely to increase, and there's a pretty good split. And they would be right. Good work, guys. Okay. So why? Does anyone want to tell me what property of snow you were thinking about? Yeah.
Oh, snow is insulating?
It's insulating. Do you remember our little piker and how they were quite happy under the snow because it was insulating? And so you're absolutely right that if that snow is insulating and preventing the soil from experiencing those really cold temperatures, then it's going to be more likely to sort of decrease our permafrost thickness. And so it's a quite complicated system. Because not only things like temperatures and snow cover, but also how much moisture is in the soil. Water is really good at absorbing a lot of energy and releasing a lot of energy. And so how much moisture is there is important. Vegetation, and vegetation does a couple of things. First of all, it's still exchanging energy and gases, but also it just provides shade. So in areas with more shade, then you might get more permafrost underneath because that sun's energy might not raise the soil temperature so much in the summer. Topography, we talked about whether it's north-facing or south-facing. That would affect our permafrost depth. Lakes and rivers, for the same reason that soil moisture affect our permafrost, because that water contains a lot of energy, takes a lot to freeze water. And so the fact that we have liquid water around is less likely to allow us to develop thick permafrost. Okay, so lastly, I want to talk about some of the really cool features that you get in areas where you have permafrost. And so the first is called patterned ground. And this is something that's absolutely characteristic of areas where you have permafrost, where you have frozen soil because of the way these things form. And we'll talk about that in a second. And then over here we have thermokarst lakes. And if you've ever flown over Canada, parts of Alaska, you'll have looked down and you'll have seen masses and hundreds and thousands of lakes. And a lot of that is because there is this permafrost that's impermeable underneath, forming our lakes. Okay. So as a reminder, this is what our ice structure looks like. It's got that sort of hexagonal shape to it, and it's really much more spread out than it would be as a liquid. And so remember, when ice freezes, it expands. And if you've ever accidentally frozen a beer bottle or something like that in your freezer, then you know this because it makes a mess and it breaks the bottle, right? And so ice and water expands when it freezes. But that's not true of, say, soil. Soil will contract as it freezes. And that funny mixture between the two allows us to develop frost wedges or ice wedges. So this is a complicated looking thing, but the explanations are helpful. So look at my top left-hand box to begin with. So in my first year, it's the middle of winter, it's really cold, and so that land or the soil contracts, and it sort of forms this crack in the soil, where it's so cold that it contracts, and it forms this little space. During the summer, when we have lots more water around, water sort of comes in and fills that crack. Okay? In my second winter, if we move on to the top right, then because that crack is filled with water, when that water freezes in the winter, it expands, forces that crack wider apart. Not only that, but again, the soil is wanting to sort of get contract, and also will create that extra space. And so when that sort of next summer comes around, again, when there's more liquid water in the surface layer, it will trickle down and it will fill that extra space that you've created in your second winter. And then if you keep going and going and going for 100 years, 1,000 years, you can develop these really thick wedges of ice in your soil. And remember, it's not going to be all the way to the top, because remember, in your active layer, you're going to have active soil processes going on, and also you're thawing it out. So you can't develop a big thick ice wedge if it sort of thaws out and melts away every year. So it's really beneath that active layer where this happens. And just to show you, I'm not making this up, here are a couple of very cold looking dudes next to ice wedges. So you can see that there's one coming down there, and that's obviously not as old a one. But look at the size of that one, it's huge. So this massive, massive ice wedge that must have taken hundreds, thousands of years to form. It's very, very cool. And we don't just get sort of one of these. Like basically, if you imagine that the soil is contracting, it's not going to just contract in one direction. It's going to contract in a number of different directions. And so what you get is something that looks something like that, okay? This sort of network, and it's very polygonal. And that's where our patterned ground comes from, this polygonal pattern of these ice wedges, okay? And in between you might have sort of piles of rocks or sort of sunken troughs where you collect water, okay? And so that's sort of one of the beautiful examples. You can see where this has happened and where the ice wedges sort of are running underneath the surface. And here's a quick image. And I want you to compare this one with this one. Where is this? Mars, okay? The same processes that we see on Earth are the things that will happen in other places in our solar system. And this is one of our first signs that there was sort of moisture in the soils of Mars not that long ago. And obviously weird things are happening, but it's still very cool that we can see the same thing on Mars. Okay. And lastly, because I know you're getting fidgety, we've got these thermokarst lakes. Okay. So these basically are thaw lakes, and they happen especially in the summer, and water collects in depressions, okay? And that meltwater is trapped at the surface, because remember that permafrost, that icy layer underneath, is impermeable. So that fresh water can't go anywhere, it's trapped at the surface. And what happens is you get more and more of this meltwater around until those lakes can join together, and then they sometimes flow or merge. Or eventually, you warm up your lake, and that manages to thaw its way through the permafrost, especially where it's thin enough, and then that can drain into that unfrozen ground underneath. Okay? Great. So we're going to talk more on Friday about what changes we're seeing. There's some extra reading this week, so have a look at it.